Hello, everybody. Welcome to Pre-Calculus, Honors Pre-Calculus. This is a permanent recording for Unit 6, Topic 2, Sequences and Series. So this is going to be a little bit longer video, and you can sort of look at what's on the page to see what exactly you need to go over, but I wanted to just make one video for the entire unit so that we had everything kind of in one place. So I hope you're doing well. I hope this video finds you well. Let's go ahead and get started with sequences. So the first question really is, what is a sequence? So a sequence within math is a list of numbers, and we sometimes refer to them as terms that are in some kind of order. So for example, you might see braces and maybe 1, 4, 7, 10, 13. Right, so that's a list of 5 terms that are in some order. Can you figure out what the pattern would be? Okay, so hopefully you've had a chance to think about it. So the pattern is that you can see that we are adding 3 each time to get from one number to the next. Okay, so that's what order those terms are in. This is called a finite sequence because it ends at some point. There are 5 terms, 1, 4, 7, 10, and 13. So this would be, n equals 1, n equals 2, n equals 3, n equals 4, and n equals 5. You might also see an infinite sequence, which is the terms might not end. So here's another example of how you might see that in set notation. You might say, all right, well, let's take the same sequence for 1, 4, 7, 10, 13, comma, ellipses, and then we put a brace here. So the ellipses indicates that it keeps going. It keeps going to infinity, okay? You might also see a sequence in some kind of formula using n. So you might see, for example, a of n equals 4n. Right? So you could list out those terms, right? So for 8, 12, 16, and so forth, but you might also see a sequence in just some sort of formula, right? So you can think about a sequence sort of like a function, but instead of your domain being maybe all real numbers like decimals and negative numbers and everything, we start in sequences with usually counting numbers. So we see that the sequence, we have n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, right? So we don't really, we have to list them out as finite terms, okay? All right. In this unit, we're really going to be focused on 2 types of sequences. And actually, we're really going to focus on this type. But there are 2 types that we cover in the unit. One is arithmetic, and then one is geometric. So arithmetic, the definition of an arithmetic sequence is that there is a common difference between the terms. So for example, if we take this initial example here, the 1, 4, 7, 10, 13, we already talked about the fact that this has a common difference of 3. Okay, and sometimes we notate that as 3, d equals 3. Okay, another example could be 20, 18, 16, and so forth. And we can see there that common difference is, you can figure it out if you want. Okay, so yes, -2, because we're subtracting 2 each time. So d equals -2. Okay. All right, and the formula that we often see for the nth term is a of n or a sub n, sometimes you'll see, is the first term a or a1 plus n minus 1 times d. So that's the formula for any arithmetic sequence. The analogy I like to think about for this is that this is sort of like has the same pattern as a linear function, right? A is your first term, okay? First term. And D is the common difference, right? So it's kind of like y equals mx plus b. D is sort of like your slope and A is sort of like your y-intercept. And if you kind of think about this first example that we did with 1, 4, 7, 10, 13, your A was 1 because that's the first term and D is 3. So the formula would be 1 plus n minus 1 times 3. So any n you plug in, n equals 1, n equals 2, n equals 3, n equals 4, n equals 5 would result in whatever term belongs to that n value, okay? Okay, the other type, and the type we're going to spend the most time on, is a geometric sequence. So a geometric sequence, instead of having a common difference, we say it has a common ratio. Okay, so an example a lot of people like to start with is 2, 4, 8, 16, 32. And let's make that an infinite just for fun. So take a moment, think about what's the common ratio there? What are you multiplying each time to get the next number? Okay, so yeah, so the common ratio is 2. So we're going to say R equals 2. The letter we use for common ratio is R, which makes sense, right? R for ratio. Okay. Another example you could use might be, ooh, that's a terrible looking brace. I got excited. All right, so let's do 27, 9, 3, 1, 1/3. What's the common ratio? What's the common ratio there? Numbers are getting smaller. How do you figure that out? All right, so as you might have guessed, the common ratio here is 1/3. You're dividing, or you could say you're multiplying by 1/3. So R equals 1/3. And a way you can tell with the ratio is dividing the second term by the first term. So if you just say 9 divided by 27, you do it in your calculator, like, oh, that's 0.333 repeating, so 1/3. Okay. All right, so the formula for common ratio, or for not common ratio, but for the nth term of a geometric sequence is A of n, or A sub n, equals your first term times R to the n minus 1. Okay, and as you might have guessed, A is your first term, just like before, and then R is your common ratio. Right, so for this example, you would have, this is 27 times 1/3 to the n minus 1. Okay, so we'll just pull that out just to show you. So A of n here would be 27 times 1/3 to the n minus 1. All right. And the analogy for, we talked about how arithmetic sequences are, you can think about them as sort of like linear functions. Okay. For geometric, those are sort of more like they follow a pattern of exponential functions. Exponential functions. So it's kind of like if you have, if your n is, is part of the expression in this way, and it's not an exponent, it's a pretty safe bet that your sequence is arithmetic. If you have n as an exponent, it's a pretty safe bet that your sequence is geometric. Okay. All right. Let's talk now a little bit about the idea of divergence and convergence just for a bit. So this goes back to connecting this with functions. So if you have a sequence and you're trying to figure out if it diverges or converges, let's talk about what convergence and divergence really mean. So let's just talk about, so let's just say A of n, we talked about that, is a sequence of real numbers. Okay, we have to establish that first. We're using real numbers and we're using a sequence. So what we're going to do is we're going to consider the limit as n approaches infinity of a sub n. Okay, and this is going to make more sense when we do an example. If the limit as n approaches infinity of a sub n is a finite number, not infinity and not does not exist, but a finite number, L. Sorry, this should say, then the sequence converges and L is the limit of that sequence. Okay. If the limit is infinite or non-existent, the sequence diverges. All right. So let's look at this with maybe some actual examples. Maybe that would help. So let's take the sequence A of n equals 1 over n. Okay, let's take the sequence 1 over n. Okay, and by the way, this is not for this won't be for arithmetic. This won't be for arithmetic sequences because since you're adding each time, you're going to go to infinity or negative infinity. This is only really for geometric sequences. So this whole piece of divergence versus convergence is just for geometric sequences, not arithmetic. So if we take, for example, 1 over n, let's play this out. So let's expand it. So we have 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so forth, right? What are these numbers getting closer and closer to? If you went out to, as n approaches infinity, what is your number going to get closer and closer to? What is A of n going to approach as n approaches infinity? 1 over infinity, right? That concept. Okay. So hopefully you got it. So the limit as n approaches infinity of 1 over n is 0, because the denominator is going to get really huge. The numerator is going to stay at 1. So you're going to get closer and closer to 0. You're never going to actually reach 0, right? Because you always have this 1 in the denominator, but you're approaching 0. So we're going to say 1 over n, the sequence 1 over n converges to 0. Okay. You can also look at this in terms of a function. So I'm just going to pop out a little thought bubble here, right? If you think about the limit as x approaches infinity of the function with domain all real numbers 1 over x, you remember from first semester and hopefully algebra 2 as well, that function looks like this. It has that horizontal asymptote at 0. So if you keep going on this function 1 over x, which has this shape, you can see graphically too, that function approaches 0 as x approaches infinity. So that's just another way to look at it. You can compare it to the function itself. Okay. Another example, we could say, let's say A of n equals 2n plus 1 over n. All right. So we could expand. Sorry, I should have put braces around this friend here. So let's take this sequence here. So let's go ahead and play it out with some numbers. So the first term would be 2 times 1 plus 1. So that's 3 over 1. Then 2 times 2 plus 1, that's 5 over 2. Then 2 times 3 plus 1, that's going to be 7 over 3, right? And then we'll just, keep going. 9 over 4, 10 over, I'm sorry, not 10, 11 over 5, 13 over 6. So if you keep going, and look at like, what is this getting closer and closer to? The limit as n approaches infinity of this function, of this sequence, is actually going to be 2, okay? It's actually going to be 2. And we can pop a little thought bubble out here to think about the graph and that idea again of horizontal asymptotes, right? And I'm just going to graph this quadrant because we don't really need to worry too much about the negative part of the domain of this graph. We just need to focus on the positive because we're starting at n equals 1 and then going forward. So we have 1, let's say this is 3. So 1, 3, and then 2, 5 over 2, right? So the numbers are actually approaching 2, okay? And you can also think about the fact that the asymptote of this function, if we just did the limit as x approaches infinity of 2x plus 1 over x, it equals 2, right? Because if you actually graphed this with all real numbers, you would have a horizontal asymptote at 2. Okay. So let's pop that little thought bubble out and we can say that 2n plus 1 over n converges to 2. Okay. All right. Another example, let's take one more example and then we'll move on. Let's say we have a of n equals, let's say 2 to the power of n. All right, so let's just do that one. So we've got 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, 2 to the 4 is 16, 2 to the 5th is 32, and so forth. Are we getting closer and closer and closer to a finite number? No, we're not. So in that case, we can just stop right there and say 2 to the n diverges. Okay. And we don't have to say that it diverges to anything. We just say that it diverges. Right. So because if it doesn't converge to a number, it diverges, and we can't say that it's converging to anything. So you don't need to say, you don't say diverges to infinity or diverges to DNE or anything like that. Just say it diverges. Okay. All right. So that's kind of like the first week of this, okay, is just about sequences. Do they, arithmetic, geometric, and all that other stuff. Are we converging or are we diverging? Okay. All right. So for the next part of our learning is series, okay, which is different from a sequence. So a series is basically adding up the terms of a sequence. Okay, so let's take our example from this first page. Let's say 1, 4, 7, 13. So for the sequence 1, 4, 7, 10, 13, the series would look like 1 plus 4 plus 7 plus 10 plus 13. Okay, so series, you just think sum, right? We're summing up the terms of a sequence. Okay. So that's the difference between sequence and series. A sequence is adding up the sequence is just listing them out with commas. And then the series we're adding, we have a plus sign, right? With a sequence, we typically use A of n. And with a series, we typically use the sum. We use S sub n, or we use summation notation, which I'm going to get into in a little bit. Okay. All right, so if you were to evaluate the series, right, like what is the sum of this series, you could use a calculator or you could just add them up, right? So 1 + 4 is 5, + 7 is 12, + 10 is 22, + 13 is 35. So the sum here would be 35, and I hope I did my math right. Let me double check myself. 23, 30, 34, 35. Yeah, so the sum of the terms in the sequence is 35. Okay. One really important thing to know about this unit is that there is a notation called summation notation, which we are going to see a lot. All right, so with summation notation, you start with a sigma, which is a Greek letter. Basically, it's the Greek S for sum. So sigma, and even though it looks like an E in English, it's in the English alphabet, it's actually a Greek S for sum. Okay, so we just have what's called a dummy variable here, like wherever we're starting. So maybe usually it's n = 1, but it's basically your index is where you start, and then where you end is just some number k, and then you use your sequence formula A sub n. Okay. So to take this example here, if we have A sub n equals, this is an arithmetic sequence because we add 3 each time there's a common difference. So A plus n minus 1d. So in this case, for the sequence that we've made up in the example, that's going to be 1 plus n minus 1 times 3. Okay, because that's our common difference in this example. You could clean that up a little bit if you want. This is 1 plus 3n minus 3, or 3n minus 2, if you'd like to write it that way. Okay, so for this, writing the sum in summation notation from this example, I'm going to put a sigma, n = 1. Our last term is n = 5 because we have 1, 2, 3, 4, 5 terms up here. So from 1 to 5 of the sequence 3n minus 2. So that's what summation notation is. It's saying take the sum from 1 to wherever you stop. In this case, it's 5 because we have 1, 2, 3, 4, 5 terms of the sequence, which in this case, our formula is 3n minus 2. Okay. So another example, we could say, all right, let's write 2 + 4 + 8 in summation notation, right? Okay, well, what type of sequence is this? Is it arithmetic or geometric? It's geometric because we are multiplying by 2 each time. So our A1 or our A is 2. Our common ratio is also 2. So taking that formula that we have from this first page, A times R to the n minus 1. So A of n equals 2 times 2 to the n minus 1. So in summation notation, we would write the sum from 1 to 3, because we have 1, 2, 3 terms of 2 times 2 to the n minus 1. Okay. All right, why don't you, let's try one. Let's try writing, if you can, please try to write 3, 12, 48, 96. Try to write that in summation notation. Just pause the video and try the problem. write the series in summation notation. All right, so we have to find the sequence formula first. So is it arithmetic or geometric? Hopefully you figured out it's geometric. You're multiplying by 4 each time. So your first term is 3 and your common ratio is 4. So your sequence is 3 times 4 to the n minus 1. Okay. So, and we have 4 terms. We have n equals 1, n equals 2, n equals 3, n equals 4. So we're going to have the sum from 1 to 4 of 3 times 4 to the n minus 1. That's that. Okay. Okay. The next thing I want to talk to you about is sum formulas. Okay. So if you want to take an arithmetic sum, okay, that formula is going to be for the sum of n terms of an arithmetic sequence will be n over 2 times the first term plus the nth term. Okay, and I'm not going to talk about this too much because this unit's really focused on geometric. I really actually want to use this time to look at the geometric sum. Okay, so the geometric sum, so I'm going to circle this. This is the arithmetic sum. And the geometric sum, I'm just going to kind of show you how it's derived so it makes sense. So for the geometric sum, you're looking at like the sum of the first n terms. Ooh, let me start over with that. So S of n or S sub n, however you want to write it, is equal to A or A1 plus A2 plus A3 plus A4, right? All the way until the nth term. Okay. So we want to figure out, well, how do we get the nth term, right? So what mathematicians figured they would do is like, let's multiply each term by like negative r, right? So if we multiply everything by negative r, multiply both sides by r. So this is negative a1r minus a2r minus a3r minus a4r and so on and so forth, right? And what I want you to think about is you can also write the S of n formula like this. So A1 is just A1, and then A2 is A1 times R. A3 is A1 times R squared. A4 is A1 times R cubed, and so forth until we get A1 times R to the n minus 1. So then let's take the negative RS of n formula, right? So that's going to be negative A1 times R minus A1 times R squared minus A1 times R cubed, so forth until we have minus A1 times R to the n minus 1 minus A1 times R to the n. And what mathematicians figured out is that once you get to these two equations, basically everything starts canceling, right? This cancels, this cancels, this cancels, this cancels, which if you add these two equations together, S of n plus negative RS of n, that's just A1 plus negative A1 times R to the n. So S of n minus RS of n equals A1 minus A1R to the n. And then you can actually divide, or actually let's factor out the S of n from the left side, factor out the A1 from the right side. And now we have S of n kind of isolated, so we can divide both sides by 1 minus R. So S of n equals A1 times 1 minus R to the n over 1 minus R. So that's actually where the formula is derived from. So I wanted you to have that just so you could kind of see how mathematicians, you know, hundreds or maybe even thousands of years ago came up with this geometric sum. Okay. All right, so for geometric sum, for example, like what is the sum of the first 5 terms of a of n equals 2 to the n? Okay, so your first term, your a or your a1 is going to be 2. Your r is also 2. So you can substitute this into the formula. You're going to have 2 times 1 minus 2 to the 5th over 1 minus 2. You're just plugging these numbers into this formula. So it'll be 2 times 1 minus 32 over -1, right? So that's going to be 2 times -31 over -1. So -62 over -1 or 62. Okay. So if you don't want to list out the terms, which sometimes you won't, especially if it's the first 13 or 28 terms, you can use this sum formula. Okay, so now we have that going. And now what I want to do is talk about another concept, which is the idea of an infinite sum for a geometric series. So the way that sometimes we introduce this is like, what if you have something square shaped? Okay, you take a half, you rip it in half, you give 1/2 to a friend, right? So you give away 1/2. So then you have half the paper left. You tear that in half and then you give 1/4 to a friend. You tear that in half, right? And then you give 1/8, right? So you keep dividing it into halves. Obviously, eventually the paper will become too tiny to tear without maybe an extremely good microscope and a very, very thin knife. You'd have to have some pretty fancy equipment to cut a piece of paper eventually. But the idea is like, if you kept doing this infinitely, how much paper would you end up giving your friend, right? And the answer would be the whole piece, right? Obviously, you can't actually go to infinity. We'll get very, 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 very close. And this is the same idea of convergence and divergence, right? If you give your friend 1/2 of a paper, and then you give your friend 1/4 of a paper or a brownie or whatever it is, and then 1/8 and 1/16 and 1/32, right? So let's add these together. So 1 plus 1/4 would be 3/4, right? Then you add 3/4 plus 1/8, and then you would get 7/8. Add 7/8 plus 1/16, you get 15/16. Then you add 1 over 32, you get 31 over 32. So you can see these numbers are getting closer and closer to 1. Okay, so if you, this is an informal way to say it, but if you took this series, and again, it's a series because we're adding the little pieces of brownie or paper. If you took this series to infinity, you would find a sum of 1. Okay, so it's kind of a neat concept. It's like, we know we can't actually go to infinity, but if we did, the infinite sum would be 1. Okay, so what I want to do in thinking about this is we'll take our geometric sum formula that we did in the last few minutes. So geometric sum, remember that formula was S of n equals A or A1. I like to say A because, you know, it's shorter. 1 minus r to the n over 1 minus r. So if you had an n of infinity, okay, if you had an n of infinity, this term would either get really, really big or really, really, really tiny. This term would get really, really big or really, really, really tiny. Okay, so I'm about to do some improper math here. If your common ratio is less than 1, for example, a half as it is here, versus if your R is greater than 1, for example, 2, okay? So let's say we're going to do S of infinity. So that's going to equal A times 1 minus 1/2. Let's say we actually can plug in infinity here, which is improper math, but I want you to kind of get the idea of what's happening here by just plugging in that infinity number. Okay, and then we'll over here, we'll do infinity, infinite sum of A times 1 minus 2 to the power of infinity over 1 minus 1/2. Okay. So if you raise a number less than 1 to infinity, right, this is going to get smaller and smaller. So 1/2 to a very, very large number is actually going to become 0. So eventually this is going to get really, really tiny. This whole term is going to get really, really tiny. But if your R is greater than 1, this whole term is going to get very, very huge. Okay. So if R, technically the absolute value of R. So if the absolute value of R is less than 1, then your infinite sum is basically just going to be A over 1 minus R, but only if your R is less than 1. Okay, because if this gets really tiny, then this is basically effectively 1 minus 0, which makes this A times 1. So the infinite sum formula is A over 1 minus R, but you can only use it if your R is greater than 1. You can only use it if your R, less than 1. You can only use it if your R is less than 1. Okay. All right, so let's try some examples. So let's say we have, let's do 4 examples because this way I'll bake some word problems into it. Okay. Let's say we have A equals 3, R equals 1/3. Let's say we have A equals 1/2 and R equals 1/2. Let's say we have A equals 1/3 and R equals 2. And then let's do a word problem. Let's say you're on a swing and it travels, I don't know, 10 meters on the first swing. And then 2/3 of the previous distance each time. Let's say you stop pumping. So in each case, we're going to say, we're going to find the infinite sum. Okay, so find the infinite sum for all 4 of these. Okay, so if you'd like to, you can go ahead and try it. Give it a little effort there and pause the video, and then we'll come back and go over the problems. All right, so with the first, it's pretty straightforward. We see that our absolute value of R is less than 1, so we can apply the formula. So 3 over 1 minus 1/3 is 3 over 2/3, which is 9 over 2. Okay, or 4.5. All right. Okay. Second example, we have first term is 1/2, R is 1/2. So we do have an R of 1/2, so the absolute value of R is in fact less than 1. So 1 over 2 divided by 1 minus 1 over 2, that's 1/2 over 1/2, which is 1, which is actually the same example that we did in that splitting up the Brownie problem, right? The first term is 1/2 and the common ratio is 1/2. Okay. Let's do this third example. So we have a over 3. I'm sorry, a over 3. A is 1/3, R is 2. Here, the absolute value of R is greater than 1, right? So this means that the sequence diverges, so cannot use this formula. Okay, remember, if your R is greater than 1, this number is going to become huge, right? So you're not going to find an infinite sum because this sequence actually just keeps going up and up and up and up. So your sum is effectively infinity, okay? So there's no infinite sum here. The infinite sum is infinity because this is a sequence that's just going to increase. Okay. All right. The last example, a swing travels 10 meters on the first swing. You swing 2/3 of the previous distance each time. So let's say you're swinging and then you just stop pumping, and each time you get 2/3 of the previous distance. So we're going to find our A, which is 10. Our R is going to be 2/3. Okay. Our absolute value of R is in fact less than 1, so we can apply the formula. So 10 over 1 minus 2/3, which is 10 over 1/3, which is 30 meters. So your total distance that you would travel is 30 meters. Now, realistically, you're not going to keep swinging forever, right? So 30 meters is really more of like a very, 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 very close approximation. Just like how in our opening problem, we talked about, 31 over 32, closer and closer and closer to 1. If you were able to take this to infinity, it would be 30 meters. But really what this is it's very, very, very close. Okay. All right, so that is our whole unit on sequences and series. I appreciate you watching. I hope that you got something out of this video, got what you needed, and I will see you next time. Have a wonderful rest of your day. Take care.